Hello friends, welcome back to You Can Do TV. One paver, 52 feet wide, laying 1,600 tons of asphalt an hour without a single joint. That number sounds impossible because for decades it was. Roads fight weather, traffic closures, and thousands of material trips just to open a lane. So it really compresses construction time without losing quality. The ending shows how a whole country builds a highway like a factory. Most roads start with a rock face. This machine skips the explosives. It cuts up to 27 inches deep and 12 feet wide in one pass, sizing rock as it goes. No blasting crew, no waiting for dust to settle. Here's where the idea gets interesting. Instead of drilling holes, packing explosives, blasting, then hauling broken rock to a crusher elsewhere, this miner grinds through the ground and leaves a ready surface behind. Tooth tips hit hard rock at the exact grade the road design calls for. 4 job steps folded into one. That is why projects using this method open new alignments weeks ahead of schedule. But cutting fast at the front only helps if what comes next does not sit waiting. Same principle, bigger scale. This unit hits around 1,000 tons an hour in softer layers, 400 in hard limestone. Drilling, blasting, separate crushing all skipped. Material goes ground to truck. The trip of rock used to take across 3 yards just got deleted. Now put that logic on an actual road job. This project widens 4.5 kilometers of highway, from 3 lanes to 4, cutting through rock walls up to 15 meters tall. The output, around 700 to 900 cubic meters of correctly sized aggregate per day, produced right where the road is being built. Excavated rock never leaves the site. All of it goes back into the embankments the road design calls for. And just like that, every haul truck the old method needed, gone from the schedule. Sometimes the terrain itself is why you cannot truck material out. At 2,800 meters up in the Alps, this dozer moved 150,000 cubic meters for new ski runs, reshaped where it fell. Try scheduling truck traffic up a mountain like that. Nobody does. Big earthworks still need big pushers. This crawler tractor sits in the 70-ton class running hydrostatic drive, so the operator gets full torque without shifting gears while grinding through rocky ground. The point on a road project is not raw power. Plenty of dozers have that. Push the right pile to the right place the first time, and nobody comes back with a smaller machine to fix it. How many of you have worked a job where the fix-up crew ended up bigger than the crew that did the original work? Now the material moves. Where does it get sized? Right next to where it came out of the ground. This plant train handles it in one continuous line. A mobile jaw crusher for the first break, a cone crusher for the finer cut, 2 screening plants sorting output, and a stacker piling it up. 5 sizes come out at once, from powder fine grit up to 22mm aggregate for anti-frost layers. Everything is on tracks. When the quarry face moves, the whole line walks with it. No foundations, no rewiring. Compare that to the old way. Truck raw stone to a fixed crusher miles away, then truck-sized product back. Both trips deleted. Fuel numbers tell the same story. Switching to mobile crushing setups cut around 50 liters of diesel per day per machine. A limestone quarry running 400,000 tons a year. That fuel used to disappear into idling trucks now It just does not get burned. Here is a smaller operator doing the same thing. A quarry pushing about 100,000 tons a year across mixed aggregates, metamorphic granite, hornfells, harder than most rock and rough on equipment. 3 mobile units handle everything. Primary crushing at the face, secondary on the cone, then a triple-deck screen and a scalping unit. 2 operators. That is it, a full crushing yard run by fewer people than most coffee shops. When the face moves, the machines move with it, and production does not stop. Cities are the hardest place to crush stone, and that is exactly where road projects need it most. This job in Hyderabad required around 800,000 cubic meters of stone, extracted with controlled drilling and blasting, plus 100,000 cubic meters of concrete for the road above. Mobile crushing was the only option. Fixed plants take permits, foundations, weeks of setup. This train, a jaw crusher, a cone crusher, and a screening unit arrives, unfolds, and starts producing. The cone crusher runs a direct drive that hit 15% better fuel numbers than the older version, uptime around 75 to 80% across the fleet, decides whether the road opens on schedule. Now the loop closes. Instead of quarrying fresh stone, this operation feeds broken concrete straight from a demolished university dormitory in Knoxville, sized down to 30mm aggregate. The tricky part is the rebar. Steel bars threaded through concrete used to be a nightmare. Loose bars jammed the chamber, embedded ones tore teeth apart. The current setup handles it, loose bar, and a side conveyor swings it out before it hits the chamber again. Big, oversized steel. And the magnet, adjustable from the excavator cab, ejects it right out. One machine has done nearly 2 million tons without breaking a blow bar. A recycled road only works if the recycled recycling machine keeps running. North of London, a rubble yard runs the same math from a different angle. A jaw crusher chews demolition waste down to a sub-40mm shingle for a wash plant, feeding cleaned aggregate straight back into new construction projects. Jaw crushing over impact was a deliberate call. Impact pulverizes material into dust, and dust is worth almost nothing. A jaw crusher just breaks the rock. You get usable stone instead of powder. Nobody buys. This operator has scaled to a fleet of 5. No long hauling to a landfill. No trucking in fresh aggregate. But save all the material you want. If the road still closes to traffic for weeks, the public does not care about your logistics wins. The San Jose numbers are worth staring at. A project scheduled for 70 working days. Finished the recycling portion in 27. Instead of 30 trucks hauling waste asphalt and hauling new material in, 5 trucks handled the whole thing. Roads stayed usable throughout. Full-depth reclamation goes deeper, 10 inches down from the top of asphalt. Cement gets pre-spread across the surface at 14.1 pounds per square yard. Then the recycler passes through, injecting hot bitumen along with water and air, foaming the mix like shaving cream so it grabs both fine cement and larger chunks of old asphalt. The result hardens into a firm but flexible base. A road life extended by up to a decade at 30 to 40% less cost than the traditional way. Some jobs need reworking the shoulder without touching the driving lane. A sideways shifting rotor lets one machine grind embankments and roadway edges up to 30 centimeters deep, 5 meters per minute. Nigeria's A2 highway between Abuja and Kano is where the scale of this idea becomes real. About 1.5 million metric tons of milled asphalt got turned into new base material right next to the highway. A mobile coal recycling mixing plant sits close to the work zone. Milled asphalt goes in, gets blended with foam bitumen, comes out as stabilized base material, sized properly, quality controlled, tested in a small lab on site before it heads back to the pavers. The old approach needed the same volume trucked from a distant asphalt plant and the same volume of waste hauled the other way. Two directions of freight, gone. Germany's oldest highway, the A555, got the same treatment. A mobile cold mixing plant produces bitumen-stabilized material at 240 tons an hour, no energy wasted, heating everything to asphalt plant temperatures. The base layer went down using a standard paver. But paving straight and paving right are two different problems. Here is the sentence nobody in road construction wants to hear. We need to redo the grade. Every time a grader misses target elevation by a few centimeters, everything downstream pays for it. Rollers come back, material spreaders come back. The paver waits with hot mix cooling in the hopper. A motor grader is the piece that decides whether that happens. It rolls and mixes material to hit consistent moisture, breaks up dirt clods for better compaction, then switches to finish grading with tight tolerances around curbs. And that same machine finishes to millimeter tolerance around a manhole. You have got to be kidding me. This is the technology answer. Set a 2% cross slope on the panel. The heel of the blade auto-corrects to hold that slope, while the operator handles the other side. That setting alone eliminates guesswork that used to require foremen standing behind the grader with a level. Bolt-on GPS masts hang 6 or 7 feet off the blade, always in the way, always risking a hit. Fully integrated 3D grade control removes the mast entirely. Three button presses is all it takes to switch modes. Full 3D GPS running elevation and slope from a design file. Rolling up on a string line for finished streets. Function, function, function. And the grader follows the string on one side while holding 3D slope on the other. A weak subgrade can stop everything. Instead of digging out an entire hillside after a landslide, this crew mixes stabilizing agents straight into the ground where it already sits. Layered soil gets bound into a load-bearing column. The slope stays. The road above gets back to work weeks earlier. Once the base is holding, big volume moves fast. These twin scrappers carry around 5 cubic yards more per pass than the older generation, burning 12 to 15 liters per hour less fuel. Reshape the corridor in fewer trips, and the follow-on crews stop watching the sky. Shoulders used to be an afterthought, dumped, spread by hand, patched later. A dedicated shoulder paver drops material straight into a pre-cut 200mm box at the edge of the road. Even depth, clean line, no rework crew called back the next morning. Not every road needs deep stabilization. A logging trail up a wooded mountain sees light truck traffic and rarely runs at highway speed. Pushing dirt and roots straight into the cut is enough. The older dozer here reshapes the slope in one continuous pass. No soil mixing plant, no cement spread, no compaction testing. The choice comes down to what the road actually has to carry. Overbuild a logging road and the budget disappears into ground no one will ever drive on again. But once you commit to a real highway grade, half-hearted compaction is where the trouble starts. The old way to check compaction was to guess, roll, guess again. then call a lab to confirm. By the time results came back, the crew had already moved on, or worse, was standing around waiting. A vibratory soil compactor in the 10 to 12 metric ton class takes a lot of that guesswork out. The drum applies both static weight and vibration, working the base into a dense uniform layer without needing a small army of testers behind it. The reason it matters for a highway schedule is simple. Every pass that hits target density the first time is a pass the paver does not have to wait on pause. Not every job needs the same compactor, which is why you pick from over 60 different models. These units cut fuel and emissions by up to 30% while pushing centrifugal force, 15% higher than the previous line. More force, less diesel, a rare combination. Here is the trick that shortens compaction from days to hours. A directed exciter system inside the drum measures ground stiffness in a fraction of a second, then adjusts how much energy the machine puts down. Soft spot underneath. More amplitude, more work. Ground already stiff. Less energy, less wear on the machine, and less risk of overcompacting a layer that is already good. The operator does not have to figure this out. The system does it. A live measuring path on the screen shows exactly where target values have been hit and where they have not. Instead of testing after the fact and hoping, the operator sees a colored map of what is done. On a parking lot job where the subgrade was failing, the crew injected Portland's cement into the base and needed to hit compaction with certainty. The roller they picked reads soil conditions through a sensor on the drum. A signal goes to a variable displacement pump, and the drum frequency adjusts automatically in milliseconds. Daily compaction tests passed every time. The operator does not fiddle with settings all shift. Has anyone watched a compactor sit idle waiting on a density lab call? Tell me how that day went. Airport runways. Sit at the top of the density specification pyramid. Slip past the joint density spec on a runway, and the surface can crack open along the seam within a season. The rollers here handle both vibration and oscillation on the same machine. Vibration for the main mat, oscillation for the hot joint, same unit, quick switch. The joint density comes together without cold seams turning into future problems. The intelligent compaction system on board tracks, pass count with GPS, and reads mat temperature in real time. The operator sees when the second pass needs to happen and at what temperature, not after. No guessing and no returning tomorrow to fix a seam that failed overnight. Here is the site where standard compactors gave up. 360,000 yards of dirt, layered with limestone and blue rock, on a 300-unit build. A 60,000-pound roller running 80,000 pounds of centrifugal force through toothed drums crushes rock as it compacts. Hold up, a roller that shatters limestone as it rolls. When a subgrade needs deep influence, not just surface compaction, impact rollers earn their keep. A non-round drum drops repeatedly as the tractor pulls it, delivering dynamic compaction and vibration in one pass. But a solid base still needs a smooth surface, and joints are where you give yourself away. The A10 ring around Berlin is 122 miles of highway carrying heavy daily traffic. Rehabilitating 2.6 miles of that ring meant one hard requirement: no joints across the full 15.5-meter width. Only one paver in the world could do it. Here is why joints matter so much. Every seam in an asphalt surface is a weakness. A place where water gets in, where freestyle pries the surface apart, where the first crack shows up. Eliminate joints across the full lane width, and you eliminate the failure point that shows up years later. The paver stretches to a 52-foot width and lays down up to 1,600 tons per hour. Behind that number sits a logistics setup people rarely think about. A power feeder receiving hot mix from trucks and blending it continuously so temperature stays uniform from one edge to the other. Cooler material from the outer sides gets mixed with warmer material in the center. A heated conveyor prevents the mix from sticking. The whole system stockpiles 45 tons of mix on board so paving never stops when a truck pulls away. Constant temperature, constant supply, constant paving speed. That is what makes a jointless surface possible. Hamburg took the same approach at wider scale. A shuttle buggy-style power feeder keeps the paver supplied continuously, letting one machine cover carriageways between 34 and 41 feet wide without joints. Trucks dump into the feeder blends and delivers. The paver behind never breaks. Stride. 41 feet wide, 12 inches deep, one pass, number seam down the middle of the road, no joint waiting to crack 2 winters from now. The right screed setup means one paver hits full width alone. Here is the American answer to the joint problem. 3 pavers running side by side, echelon style, all feeding off shuttle buggies. The Minnesota project on Highway 77 eliminated at least 25,000 feet of paving joint on a mill and overlay. Instead of laying one lane, letting it cool, then paving the next against a cold seam, all 3 lanes go down hot at the same moment. The seams bond while the mix is still workable. Thermal mapping on the pavers reads mat temperature with a laser and displays it live. Intelligent compaction on the rollers tracks past patterns with GPS, so no spot gets overrolled. Feedback used to take days from the lab. Now it takes seconds from the screen. British Columbia went further, 4 pavers wide, a 62-foot echelon spread across the highway, with rollers trailing behind, working through the night with 95 people on shift. One continuous pass, no cold joint anywhere in the mat. A Formula One track leaves no room for a bad surface. Cars run downforce loads on rubber compounds that will punish any bump the paver leaves behind. The Austin bill called for pave widths up to 42 feet 8 and laydown rates up to 1,200 tons per hour. The Ergo Plus operating concept lets the operator hold precision at those widths without constantly adjusting. A powerful engine keeps output steady across long paving runs. Race surfaces are unforgiving of small errors. The paver has to be more precise than the car it will eventually carry. Airports do not build, they race. A runway shut down for repair means canceled flights, rerouted freight, and a countdown clock nobody stops. At Naval Air Station Jacksonville, rehabilitating the 1028 runway meant hitting density numbers most highway jobs never see. The paver was custom built for the job. A track machine with a specialized screed, all outfitted with GPS control, and the runway's design model loaded straight into the paver. The result? Density readings around 89% right off the back of the screed, hitting the specification without a rework pass. On a runway job, hitting spec on the first pass is the difference between opening tomorrow and opening next week. Frankfurt moves 60 million passengers a year through its runways. Fixing a bumpy takeoff surface meant working overnight windows only. A surface scan built a 3D milling model. The mill cut to that model, paving started before dawn. Everything on the ground had to move before the first inbound. A 6.5-kilometer stretch of the A480 Germany faced the clock pressure highway crews live with every summer. 51,000 tons of asphalt had to go down across an 11.4-meter width without joints. The setup: one big paver plus 2 material feeders working in parallel, both dumping into the paver's hopper. Trucks never stack up. The paver never pauses for material. That is what a jointless surface really requires. Not just a wide screed, but 2 supply lines feeding it at production rate. A rural agricultural road behind a Dutch dike had to be back in service fast. The old surface got granulated in place, mixed with foamed bitumen, then paved straight back down. 2 machines, 1 continuous pass. No landfill trip, no fresh aggregate delivery, no extended closure. Concrete paving at an airport is a different animal from asphalt. Airport slabs need to handle repeated landings at commercial weights and hold flat for decades under desert temperature swings. At Phoenix Mesa Gateway, a 4-track slipform paver ran the pour with a texture and cure machine following behind. The augers distribute concrete evenly across the full slab width. The slipform screed shapes it. The trailing unit textures the surface for aircraft tire grip and locks in the cure compound before the concrete starts drying too fast in the Arizona sun. 1 continuous mobile line producing a runway grade slab as it walks forward. Air Force Base paving comes with a specification list that reads like a legal document. Load ratings for fighter aircraft, wing footprint tolerances, and joint patterns designed for jet blast, all of it locked into the paver's design model before the first bucket of concrete arrives. The slipform paver here handles wide pour slab work in a continuous strip. Concrete goes in one end, formed and finished slab comes out the other, all shaped by the machine as it moves forward. No side forms to strip. No wet slab sitting exposed while somebody comes back with a trowel. The pour keeps moving because the base cannot afford to wait. Regional airports face the same pressure as major hubs, just with smaller crews and tighter budgets. At the Cedar Rapids Airport, a slipform paver laid concrete for a new pavement section while the rest of the airport kept operating. The machine pours, shapes, and finishes in 1 continuous pass. Workers alongside handle edge finishing and joint details as it moves. A mid-size airport cannot afford a closure that runs over. Every extra day pushes airlines to look at nearby fields. But once the concrete is down, the old surface still has to go somewhere. Pikes Peak Highway sits at 14,000 feet, with running grades up to 12% and cross slopes near 8% on the switchbacks. Standard milling machines lose horsepower at that altitude. An 85,000-pound cold planer with a twin-turbo engine pushes through where lighter machines cannot even reach target depth. Cuts range from edge milling to full depth, all on a schedule that gives the crew a day and a half to finish. Working machines up a mountain like this feels less like construction and more like a mission with a deadline. Down at ground level, the same machine handles a different challenge. Reconstructing 2 miles of road in an Illinois mobile home park meant 5-inch deep cuts at 90 feet per minute. 10 to 12 inches of pure asphalt, no rock, and the machine does not slow down. That is the kind of number that changes bid schedules. Airport milling brings tolerance requirements down to 2/100th of a foot on runways. Paired with a robotic 3D control system, the cold planer holds that tolerance all day long. Slope degrade the engineering secrets. Slope degrade switch happens without stopping. Sarasota's taxiway milled to spec with the paving crew already lined up behind. Not every rebuild has to be asphalt on asphalt. On Route 58 in Virginia, the existing concrete pavement was shot blasted to remove oil and debris, then overlaid with continuously reinforced hydraulic cement concrete, no joints across the surface. Steel reinforcement running through the slab keeps cracks tightly closed. The finishing crew grooves the surface for tire traction and drainage. Expected lifespan, 30 years. That is the alternative some road agencies are moving toward when oil prices swing hard. When the pavement itself lasts 3 decades, the whole project schedule looks different. Look at a modern paving site. From above, and it stops looking like construction. It looks like a factory that walks. On Interstate 70 near Le Mans, a 4-track slipform paver lays concrete 38 feet wide, 12 inches thick in 1 continuous pour. Dump trucks feed the paver in sequence. Augers distribute the concrete evenly. Screeds shape it. A dowel bar inserter drops the load transfer steel automatically as the machine moves. No crews walking wet concrete to place them by hand. The final finish trails behind. Curing compound goes on. Yards of finished interstate pavement per hour. Everyone in the crew has a station, and the station moves. Now stretch that idea across a country. The Autopista Al Mar in Colombia runs 176 kilometers through mountains, cutting up to 76 kilometers through mountains, cutting up to 70 meters into terrain, with 35 bridges and 5 kilometers of tunnels, all coordinated as one project. And here is the number that ties this whole video together. On the A2 highway in Nigeria, 75 machines worked as one integrated production line. Soil stabilization with cement, milled material crushing and screening, cold recycling into base material, paving, rolling, all feeding each other. Paving, rolling, all feeding each other. 1.5 million metric tons of milled material recycled. 71,000 cubic meters of concrete. 2.4 million square meters of finished road. Good gracious, that is a whole factory on the move. That is a modern road build. Speed comes from turning a construction site into a factory. Here's what the industry is quietly arguing about right now. As machines get smarter and job sites turn into moving production lines, one number keeps coming up in construction offices. How many skilled operators will still be needed on a paving crew 10 years from now? Some contractors say automation is the only way to keep up with the workforce shortage. Others say the best roads still come from experienced hands who know what a bad subgrade feels like through the seat of the machine, and no sensor replaces that. If you were building a highway crew today, would you invest more in automation or more in training operators? Say your thinking in the comments. Which side has the stronger case in your view? Thanks for spending the ride with this video. Subscribe if you want the next deep look at how heavy industry actually gets built. Take care.